Okay, I wanted to cover my physics simulation. I just recorded this, but I realized that I had a few mistakes. Not like mistakes talking about the code, but like mistakes talking about the physics, and that kind of bothered me. So let's just make gravity a bit larger and run the simulation. As you can see, this mass is pulled into each other, and whoa, whoa, yeah, insane. I know I'm the goat. Uh, you can tell me later. But yeah, this isn't the best, right? But I just thought it was pretty cool. It was a project I made. It took like a few hours. So yeah, because this is my first ever C++ project. Okay, okay, okay. Now that I'm not getting flamed, okay, let's talk about it. So the rendering library I decided to use was Raylib. Personally, I'm not too interested in OpenGL because I don't really want to learn graphics rendering. Personally, I intend on going into software engineering rather than game development. I enjoy coding as a practice. I enjoy coding like itself, but I don't really enjoy game development. Anytime I've tried it, I never enjoyed it. So I think it's better for me to try and just learn, like, whoa, I dropped something. Learn this more, like, this stuff which is more applicable and this more problem related stuff, like problem solving stuff and math stuff and physics stuff, rather than this rendering stuff, which kind of only matters if you plan on rendering stuff, which I don't really ever plan on doing, or making a rendering engine. So here I have my first function called, or defined, which is the distance between centers 2D, right? And then it's just finding the distance between centers, which is just going to be the distance 1 minus the other distance. Doesn't really matter. And then you take this, right? The distance on the x-axis, the distance on the y-axis. Then you use the distance equation or just this hypotenuse function in C++, and you go dx, which is distance x, comma, dy, distance y, and you get your distance. So yeah, it's pretty easy. And then basically the same thing, just in the third dimension, is colliding. This is really simple too. If you see here, it goes this if return distance, whatever. All this is doing is like, okay, well, if the distance between centers, between you and this other body, is less than your combined radius, then you must be touching, right? Because then that would mean the radius of these two objects, right? If they were, if the distance, okay, if the radius of these two objects were combined, right? And that was their distance, and that was the distance between the centers, then that would mean that they were touching. If they aren't combined, that means that they're intersecting, right? Because if you think about it like this, if you have one circle and you have another circle and you put them right next to each other, right? And you want to figure out, well, what's the distance between the centers of these two circles? It would just be the combined radius. But if you then overlap them somehow, let's just say you can like phase through stuff, you overlap them, right? And you like phase one into the other, then the distance would be less than the combined radius. And that would show that they're intersecting. I feel like most people would understand that. It's very intuitive. It's kind of like common sense, but I kind of just wanted to explain it. So the apply collision response, you'll see this for loop in my gravity function too. This is basically saying, okay, so there's already this argument which is requiring me to have this list of all the celestial bodies. And so for the entire length of this list, let's just go through it and check every single one where I is the number that we're on, or number minus 1. So if you're on like the 5th body out of 100, then I would be equal to 4 because you're starting at 0, but that's not really too important. So it's like, okay, rather, the only way you can do this is like you check each one individually. So like you go, okay, is my gravity with this one okay? Yep. Is my gravity with this one okay? Yep. Is my gravity with this one okay? Yep. Where's my collision with this one okay? Yep. Is my collision with this one okay? Yep. That's basically what this for loop is doing. So it's pretty useful. When I first learned about this, I was like, yo, like, this is so, like, why was I not thinking about this? Then I defined the celestial body, other body, is equal to other I. As I already explained, I is the celestial body which we're on in the list. So other I would be the current celestial body. This prevents me from just having to use more brackets and saving time. So I define theta, which is arctangent of the other body on the y-axis and my position on the y-axis, comma, other body on the x-axis minus my body on the x-axis. Basically, this is saying the y distance and the x distance, and is finding the tangent of that, the arctangent of that. So the arctangent and the inverse trig functions in general, not like cosecant, but like arctangent and stuff, they're useful for finding unknown angles. If you take like geometry, I think you learned this, but you might not remember. Phi is what I'm using for the third dimension, like crazy stuff, which is basically the same thing. You kind of just, the only difference is I'm using a third dimension angle rather than a first one. And this is between centers 2D. So it's like, okay, this is 2D, this is 1D, this is 3D, this is 2D. Think about it like that, I guess. So this here is saying if the other body position, which is the current one that we're on, the current celestial body that we're checking to apply gravity to, is equal to my position, then continue. Don't do it. Don't do this. That's because if their positions are the same, that must mean that they are the same object, because two objects in this simulation can't have the same position. So it's just an easy way to be like, okay, well, I shouldn't be checking to apply gravity to myself. That's not how gravity works. This isn't how gravity works either. So, but that's not how Euclidean gravity works, or whatever, however you'd call it. Isaac Newton's idea of gravity. So before we collide, right when we collide, I save my positions. Then, right, say with me, this is going to be really easy. I set my x velocity to my mass times my saved velocity, which is literally just my velocity at the collision, plus my other body mass times other body velocity, divided by mass plus other mass. And basically the same thing for all of this. I could have made this smaller. I didn't, though, because I genuinely forgot. But you can do this all in like way simpler with just a for loop. You don't have to write out all three of them. Basically, right, this is mass times velocity. Mass times velocity is momentum, or P. So P1 plus P2, which is P total, divided by mass 1 plus mass 2, which is the total mass. So basically, I'm dividing my total momentum, or PT, over MT. And that's going to give me my total velocity. And the total velocity is shared, so they'll both get the same velocity, if you know what I mean. It's very simple. This overlap right here, all this is doing is preventing objects from intersecting. That's because in real life, objects don't intersect. If I punch my hand, I don't think my hand phased through my other hand, It's not passing through. That's because of the normal force. Electrons are keeping us from passing through. The electrostatic force is way stronger than gravity, too. So it's like objects don't just phase through each other. No. We're prevented from doing that because electrons are repelling each other. But I can't really model that here. And if I can, I might not know how to. I'm going to be honest. But I decided to represent that with just something to prevent us from over from colliding. That's why I define theta and stuff here. I don't really want to cover this because it's kind of boring. It's kind of boring, and also because I cover the sine, cosine, and theta stuff in the applied gravity section. Ooh. Okay, so I define these. I define distance, and I define force. Force is gravitational constant, 6.67 times 10 to the negative 11th power, times mass, times other mass, over distance squared. It's actually distance between centers, but it's the same thing. I'm doing distance times distance because that's what squaring something does. You multiply it by itself. So then I set my acceleration on the x, acceleration on the y, acceleration on the z. Acceleration on the z is equal to cosine of theta times force divided by mass. If you know, a force causes a mass to accelerate, and that's why force can be expressed as F equals ma. And as my IDE is telling you, you can derive acceleration from that as A equals force over mass, which is very simple. So I'm just dividing the force by the mass. Very, very easy. Then I have this cosine theta, right? Because like imagine you have a ball, right? And you apply 1 Newton of force to this ball, and then that ball somehow got 1 Newton applied in west and 1 Newton applied north. That wouldn't make sense, right? If it had 1 full Newton applied to both, that would you would be like, I don't know who you'd be like, but you'd be creating force out of nowhere. You'd be like breaking the laws of physics with your punches or something. You'd be insane. But basically, right, this cosine of theta, it's like, okay, so the x and the y-axis aren't going to have the exact same amount of force in newtons. It's not going to be like, you're not going to divide. You're not going to be like, okay, well, there's 3 axes, so let me go. I apply 1 Newton of force, so that's 1/3 on the x-axis, 1/3 on the y-axis, and 1/3 on the z-axis. No, you don't do that, because that's not true, right? If you look at a circle, right, and you have a force, right? You apply a force at an angle of 30 degrees. You'll have 1/2 on the y-axis, right? And you'll have square root 3/2 on the x-axis if you apply the force at 30 degrees. So you don't just divide by 3. You use these basic trig functions, which almost everyone knows, to do it. So this theta, which already is defined, is the angle between the two bodies. So, and phi is also the angle between the two bodies on a 3D scope. Basically, cosine and sine really are good for 2D, and like they're the goats with theta. But you can't just use, like, there's no 3D trig function really, so you wouldn't be able to just be like, okay, sine theta. That wouldn't make much sense, would it? We have to use another variable, phi in this case, to find a 3-dimensional angle. And sine of phi is the force. Very simple, very simple. Because phi basically in this, it's like longitude, latitude. So it's like the phi would be going along like the height of the earth, kind of, if that explains it. And then this for loop is the better way I could have done this instead of being lazy. But for int I equals 0, I less than 3, I plus plus, velocity I, because you'll check through 1, you'll check through 2, you'll check 3, you'll check through them all. Acceleration plus equals, or velocity plus equals acceleration, because that's kind of how it works. Velocity increases with acceleration, and then distance increases with velocity. That's why distance increases quadratically with acceleration. So on Earth's gravity, if you were to graph object falling from rest, it would be quadratic, not linear. But if you were to graph its velocity as it fell from rest, it would be linear. And if you were to graph its acceleration, since there's no real jerk on Earth, it would also be linear, but it would be like a 0. It wouldn't change. It would be constant. So yeah, that's basically my program. It's very simple. I just wanted to document this. I didn't even use this. I thought I was gonna use this. But yeah, this is the first C++ project I've made like ever, besides like a console app when I was like 12 or 13 maybe. So yeah. Yeah, my chair fell. Have a nice day.